We've made it now to our final topic in statics, which is moment of inertia. So while it's really exciting that this is the last thing we have to learn about, this moment of inertia, I would say it might be our hardest topic yet. This is really kind of a difficult topic for students to grasp just because there's no real world version of it. It is a hypothetical geometric term that we use to talk about moments of an area. Really, this is also called second moment of an area. So sometimes you'll see it referred to as second moment of area, because this moment of inertia that we're talking about is not the same one that you had learned in Physics 1. So in Physics 1, when you talk about moment of inertia, you're talking about something with mass, right? You have that, I think it's I is mr squared. There's usually one way you see it. But this moment of inertia is different. This is a term of geometry. It has nothing to do with the mass. It is this second moment of area. It's a different concept altogether, but it sometimes gets confused with that because people will often refer to this as moment of inertia as well. But this moment of inertia that we're going to be talking about is when you have some geometrical object, something with a shape, some kind of shape that we're dealing with. Typically it's a cross section. If we're looking at something in 3D, we're going to look at the 2D cross section, just the area of something. And we've got our little area differential, right? And some x distance and y distance to this area differential. And basically what it is it's a geometrical property that's going to be used in future calculations, but it has no real world meaning whatsoever. And one way I can kind of explain that is that the units for this, when we go through this equation, the units that you end up getting at the end are going to be in to the power of the fourth. So like inches to the fourth power, or millimeters to the fourth power is something that we see a lot. So we can think like, if you have inches squared, that's an area. If you have inches, that's a length. If you have inches cubed, that's a volume. But inches to the fourth is now in this dimension that we can't see, right? So it's just a property of the geometry that we really don't have a visualization for. It's beyond our human scope of knowledge right now. And all it is it's a property that we need to know to apply into future equations so that we can figure out more properties about the geometry that we can actually use in real life. So mostly this gets used as steps in other equations in the future that are actually useful and have real world meaning. But let's talk about these equations actually, right? So moment of inertia can be taken from the x or the y axis. So if I want to take my moment of inertia about the x-axis, this is the I is the moment of inertia, and then the subscript x just tells you that it's about the x-axis, and we're integrating over the area of y squared dA. Y squared dA. So our y equation, then dA. Or our moment of inertia about the y-axis, going to be the integral of our area x squared dA. These are our basic integral equations. If we want to do it about the axis. So about the x-axis, we would use this one. About the y-axis, we would use this one. Or we could find both using the polar moment of inertia. So polar being, if we recall, having a radius, polar being something round, using your sines and cosines, something circular. Our polar moment of inertia is represented by J about the origin, and that's going to be the integral over A of r squared dA. But we can also write this as Ix plus iy. So these two terms added together, these basic integrals added together. And we use these basic integrations whenever we are taking slices that are parallel to the axis of interest, right? So if I wanted to take my I of x, my moment of inertia about the x-axis, then I want to use the one that is parallel, right? I want to take a differential slice through my area that is parallel to that axis. So that meaning that my slice goes through like this. And if I want to do my I sub y, then it has to be parallel to the y-axis. So I would take my slice that looks like this, my differential slices. It's still going to work like centroids where we're taking integrals and taking these differential slices. We notice that the equations are even a little bit similar, but now instead of a term on top and bottom, it's just one term and it's an x squared or a y squared term. So that we end up with these units that are to the fourth power. So this is when we use the basic equation, basic integration equations. And it'll make a little more sense with practice, but it takes a lot of practice because these integrals can get really messy. But the main takeaway is that if you're going to use these basic integration equations, you need to take these differentials parallel to the axis of interest. If they are not parallel, for example, if I wanted to do I sub x, but I wanted to use this differential right here, I have to use a different equation. I cannot take this slice just using the basic integration equations. I have to use something else called the parallel axis theorem. So this means that I am not taking it, right? If I want to use this, my parallel axis theorem, give some space over here. Now my I sub x is going to be I sub x prime. This represents the centroid. We'll talk about that in a second. Plus a d sub y squared. And our y1 is the same equation, just with y's. A d sub x squared. Let's break down this parallel axis theorem. And what do each of these terms mean? So we have a table in our book that gives us some basic centroids of common shapes. For example, a rectangle has a moment of inertia. If we look it up in the table, find my table here. For the, let's say I sub x. I sub x for a rectangle is going to be 1 over 12 bh cubed. So what this term is here is the moment of inertia for your differential slice, for the slice that we're taking, about the x centroid. So that's why it has the bar on top of it, like our centroid. And then that x prime says that we're taking it about the centroidal x-axis and not the regular x-axis. So meaning that we're taking, instead of a centroid about this axis, this is about the centroidal x-axis. So these all come from tables. You do not have to calculate these two terms for x and y, moment of inertia. They are not anything you have to calculate. You're just going to look them up from the table, and it's pretty much always going to be this rectangular one, because our differential slices are almost always rectangular. We really don't work in 3D for these. We're always working in 2D. So it's going to be 1/12 height times base cubed for the y1. So these are the two main equations that you're going to be plugging into one of these two terms. So that's the first part of the parallel axis theorem. And then this next term, a d sub y squared, is a little bit more complicated. This a A is area, we know that, so that's easy enough. That's the area of our differential slice, right? Just our length times our width. But this dy term can get a little confusing. The dy and dx terms. All they are is distance to the centroid from your axis of interest. So often when we were doing centroids, we were calling this distance y tilde or x tilde. So if you're taking them from the x or y axis, it's the exact same as y tilde or x tilde. So d sub y equals y tilde and d sub x equals x tilde. If you are finding the moment of inertia about the x-axis or the y-axis. But if you're finding it about some other axis, like the centroidal x-axis or centroidal y-axis, then it will be different. But for most cases, we're taking our moment of inertia about the x-axis or y-axis. So where we take it matters because it changes these dy and dx terms. And we'll kind of break this down again in an example so that way you can see where these numbers we're pulling are coming from, where each of these parts of the terms come from. But again, it's similar to centroids. It's just a little more convoluted, right? There's usually a lot more steps. To add another layer of complication on top of that, often we don't see these two equations as just equations. We typically have to do them as integrals still. So you will sometimes see these equations written as, delete this real quick. You'll sometimes see these equations also written as our I of x for parallel axis theorem being the integral of, let me find it real quick, make sure I get this right. Our integral, oops, of d I bar x prime plus dA d sub y squared. So you'll often see this as an integral because we'll sometimes have since we're taking these differential slices, you're going to have a dy or a dx term that enters into both of these. So we're still going to have to take integrals with our parallel axis theorem equations. So again, we can use these basic integrations whenever we are taking differential slices parallel to the axis of interest. And our problems are going to tell us our axis of interest. And almost counterintuitively, we use the parallel axis theorem anytime the differential slice is perpendicular. So again, it's a little bit convoluted, but our steps are going to be very similar to how we calculated centroids. So we're going to be given a shape, and then we're going to have to pick out all of the components that we need to build these equations, depending on which axis and which differential slices we're taking. So we'll have to pick a differential slice, just like we did for centroids, pull out all of our information, and then perform the integrations. So a similar process, just a little bit more convoluted. But let's take a look at an example and see how this works. So in this example, it asks us to find the moment of inertia about the x-axis for this area shown. And we have two ways that we can go about doing this. We can either use the basic integration method, so that's the first two equations that were on the left side, or we could use the parallel axis theorem, and those were the two equations that were on the right side. So we have to pick one of those methods, and the way we do that is by picking our differential slice. So if we want to use the basic integration equations, so that was our moment of inertia about the x-axis, that's what that I sub x stands for, is going to be the integral of y squared dA. So if I want to use this basic integration equation, I have to make the slice parallel, right, for basic integration. So what that means is the slice I have to take has to be parallel to the x-axis, meaning that my slice needs to be something like this, right? So now from this slice, I can start pulling out information to go through this integration. So I want to use the basic integration. I have my slice parallel. Let's start pulling out the information from that, right? So my differential is going to be that dy. He's the little side here. My length here, I have this distance here is going to be x. And so this distance of my full thing is going to be 100 minus x. Right, so that's the length of this side here. And that's just because he's not touching that left side. He's not touching the y-axis, so he has that little more, grody looking equation. So I have my little differential slice. So what's the information that I actually need to pull out here, right? If I know what this dA is now, because I just found the length and width of my rectangle, so my dA, in this case, dA is going to be that 100 minus x times dy. If I put that into my equation, the integral of y squared times 100 minus x times dy. So I know I need my whole integral in terms of y terms, and they give me y squared equals 400x. So therefore, my x would equal y squared over 400. And I can substitute this guy right into there, and then I should be able to do my integration. So my integral is going to be over the total y length, right? So that's 0 to 200 of y squared times 100 minus y squared over 400 dy. So that's the full integral. And then I go ahead and just perform my integral calculations, and I get my moment of inertia. If I do the integral portion, 100y cubed over 3 minus y to the 5th over 2000. And when I evaluate that from 0 to 200, you're going to get a really, really big number. And don't be surprised by that, because again, the units are going to be millimeters to the 4th, right? So I had these in millimeters. I'm already working with 100s and 200s really high. And now I'm taking those millimeters to the 4th power. So I'm going to get a huge number here, which in this case, I got 1.067 times 10 to the 8th millimeters to the 4th. You can write out the full thing. You can write it in the shorthand scientific notation like I have here, whatever makes the most sense to you. But a lot of times these millimeter to the 4th power are going to give you huge numbers for moment of inertia. So this was one way to do it, right? This was the taking a slice, we did the basic integration equation, but what would this look like if we used the parallel axis theorem instead? Because we could solve it with either. Both are totally acceptable ways to solve it. It usually comes down to if the problem asks you to solve it in a specific way, or if one of the integrations is substantially easier to do. So let's take a look at how we would do this with the parallel axis theorem. So I'm going to go ahead and delete, I'm going to delete all of this, and we'll look at this parallel axis theorem, which our parallel axis theorem said, this in blue sounds good. I sub x is the moment of inertia about the centroidal x-axis for our differential slice, plus area times distance from the centroid to y squared. And again, we often see this as an integral. So this is going to be integral di prime plus the integral dA times distance, not a differential, distance y squared, distance to the centroidal y squared. So now let's break down these terms and figure out where these would go. So we're using the parallel axis theorem. So for parallel axis theorem, we need perpendicular slices. Perpendicular slices. So that would mean, since we're still finding this about the x-axis, a perpendicular slice is perpendicular to the x-axis. Pretty self-explanatory there. And now we just need to break down what these terms are and how we find them. So our slice here now has a width of dx, and the height here is just y. So let's look at all of these terms that I need. So we said this term here comes from the differential slice itself and from the table. So from the table, we said that for a rectangle, it is 1/12 b h cubed. So we need to find what this b and h is for our specific circumstance. And for us, our base is the dx, and then that height is the y value, right? So again, just pulling that from the slice. So this means that for us, we have 1/12. Our height was y, so y cubed, right? That h cubed became y cubed, and the b is dx. So I just flipped their placement there. But this becomes our term that we put in here, and we can see obviously we're going to have to do an integral because of this dx term, right? Because of that little differential. So we know we're going to be doing an integral there, and this is our component for this section here. So what about our components for the other half of this equation, right? So what are these components? We need a dA, which our dA, again, is pretty simple. We pull right from the slice. Area is base times height, so it's just going to be y dx. So that takes care of the first term of our second guy here. And then we need this d sub y squared. And again, this is just the distance to the centroid. Anytime you're taking it about the x or y axis itself, d sub y is just going to be that y tilde value. So now we need to go back and take what we know about centroids to find what the y tilde value is. And remember how we get that is our centroid here. To find the y tilde value, it is just the y distance to the centroid, right? So this distance here is going to be y over 2. And so for us, this is y over 2. And now all I need to do is make those substitutions into this equation. So my moment of inertia about the x-axis is going to be this term I had here, which we said was the integral. Now, since I'm taking it this way, it's from 0 to 100. 0 to 100, 1 over 12, y cubed dx, plus, same integral since we're doing dx, 0 to 100. We could make it all one integral if we want, of our dy squared times dA. So y squared, or y over 2 squared, right? That's our dy term, and we need to square it, times our dA, y dx. So this is my full integral now. This is the integral that I have, and I can go ahead and simplify it and then just evaluate the integral. If I simplify this down, I know that since they have the same same end terms, same dx. I can go ahead and combine this all into one integral. This is going to be from 0 to 100, and if I simplify all these terms down, I actually get 1/3 y cubed dx, and of course my y squared equals 400x, so I need to plug that in for my y value. So I get the integral from 0 to 100 of 1/3 times 400x to the 3/2 dx. So now I would just go through and evaluate this integral. And when I evaluate the integral, I'm going to find that I get the exact same answer. Right, so I get that 1.067 times 10 to the 8th millimeters to the 4th. So it didn't matter whether I used the basic integration equation or this parallel axis theorem. It was kind of just whatever was easiest, whatever integral was going to be simplest for me to calculate. So you can do this in either way. It's good to get practice doing it both ways though. But what if I wanted to find this about the y-axis? How would I do this any differently? Right? I would still be doing the same things. I could do it by basic integration equation, or I could do it by parallel axis theorem. So let's look at that really quick. Right, what if I wanted to do this from the y-axis? Now let's, whoops, cross that out and just say y-axis instead. So for my basic integration equation, IY, moment of inertia about y, is the integral of x squared dA. So now my parallel one is the blue one, right? So now this blue guy, so use blue slice now. So we had used the blue slice for the parallel axis theorem because it was perpendicular to the x-axis, but now that is parallel to the y-axis. So I'm going to be pulling information from this guy. So we just pulled this information, right? dA equals y times dx. This is our blue slice information to do the basic integration. And what else do I need? So I have IY equals the integral, again from 0 to 100 of x squared y dx. So really all I need is I need to substitute in this y here, and I know that y squared equals 400x. So I get IY equals the integral from 0 to 100 of x squared times the square root of 400x dx. Right, and I can plug that into my calculator or into some integral solver to go ahead and cut myself out a couple of steps, especially when these integrals get really hairy. It's good to practice doing integrals by hand, but to double check yourself, I really would recommend using a Mathway or Symbolab or Wolfram Alpha, whatever website you like to use to check your integrals, because they can get really big and messy with these moment of inertias. So check yourself that way. It's good to practice your integrals, but this isn't a Calc 2 class. I'm not testing you on whether you can do an integral. I'm testing you if you know how to set up these integrals well, and then to the much smaller degree whether you can evaluate them. But the setup is the most important thing here. So our moment of inertia of y, when I plug this into a calculator, I get 5.714 times 10 to the 7th millimeters to the 4th. And that came from my basic integration equation. So it's again, can you set these up? Can you pull out the slices that you need and pull out the information that you need to do these integrals? Let's look at how this would look with the parallel axis theorem. Whoops. So that was the basic equation for the y-axis. I'll leave my answer down here just for reference. But now I would be going back to those yellow slices. So now I'm doing parallel axis theorem for the y-axis. So that is my I of y equals my centroidal moment of inertia plus a times d sub x squared. So now we'll pull out all of these terms. So our I sub y prime, our centroidal x-axis, given to us from the table, is our 1 over 12 h times b cubed. And so what's our h in this situation? We're pulling again from our yellow block over here, the horizontal one that is perpendicular to the x-axis. Okay, so this is perpendicular. So our height is our dy term. And our base is our 100 minus x. So I can already tell you this integral is gonna look pretty nasty, right? If I plug this in, I have Iy equals integral 0 to 200, right, this distance here, of 1/12 100 minus x cubed dy. And that's only this first part. We still have to find this whole term. So this is only going to be one part of this equation. We can already see there's going to be like u substitutions, or in this integral, it's going to be much nastier to evaluate than that basic integral equation. So at this point, you might even say, oh, maybe I don't want to do parallel axis theorem, just do the basic equation one. Like, it can be very helpful to yourself to go ahead and start both of these and see which integral is going to be a lot more complicated for you, and do the easier integral. But let's go ahead and look at this other term, how we would set this up. So our other term, right, is we're doing integrals, so this is actually, whoops, dA, right, dA, and that's our area of that yellow rectangle, is 100 minus x times dy, and the d sub x term is our centroidal x distance. So now I want to know, right, here in purple is going to be my centroid of the yellow. So my centroidal x distance here my x tilde is going to be x plus 100 minus x over 2, right? We saw some equations like that when we were doing centroids. So again, this is going to be kind of a messy integral, right? X plus 100 minus x over 2. So now if I add all of this into my equation, right, this is the equation we were looking at down here, plus my a, right, so I'm going to do this x squared term first. So this is squared. X plus 100 minus x over 2 squared times 100 minus x dy. So this is the full integral, and I need to substitute in y's for all of these x terms here. X term, x term, x term, x term. All of those I need to substitute in x equals y squared over 400. So now if I look at that full integral that I'm doing, oh boy, it is a big, long, nasty integral. I'll write it out, but we are certainly not solving that. Oh my gosh. It's going to be so large. Okay. Iy equals the integral from 0 to 200 of 1/12. Oh my goodness. 100 minus y squared over 400 cubed plus y squared. I'm not even going to have enough room for this one, I don't think. Hold on. We'll have to put that down lower. Oops, oops. Yeah, we'll put that on the next line. Oh my goodness. Okay. Plus y squared over 400 all over 2 plus 50 squared times 100 minus y squared over 400 dy. So this is the full integral we would get using parallel axis theorem to do this about the y-axis for that yellow slice that we took. This is disgusting. This is a gross integral. Don't try to do this by hand. Plug that into a calculator if you get to that point, because this is a monster. It would be so much easier, and you save yourself so much time with that simpler integral we did using the basic integration equation. So it's kind of like centroids in that picking your differential slice really makes a difference in your life on how tough the integral you're doing is going to be. So for this last example, I want to touch on polar moment of inertia, which, if we'll recall, polar moment of inertia is represented by J, and it is about a point, typically about the centroid. So here we have this Pop-Tart shape over on the left side, and it's just a standard rectangle with a base B and a height h, and we want to know the polar moment of inertia about the centroid. So sometimes it'll be about the origin, JO, or it'll be about the centroid of the shape, right? We don't have to just do it about the x or y axis when we're doing these moments of inertia. It could be about something like the centroidal x-axis, centroidal y-axis, in this case, the centroid. So our polar moment of inertia is our ix plus iy, right? Just adding together those moments of inertia about each axis. But again, since this is about the centroid, right, not our standard ones, it is the centroidal iy and ix for JC. So what this means is that we can pull these two values from our table of knowledge, right? This is just a standard rectangle. It's just a standard shape. We can look up the moment of inertia for it in our table. And when we do, we get that our moment of inertia about the centroidal x-axis is 1/12 bh cubed, and for the centroidal y-axis is 1/12 hb cubed. And notice it leaves it in terms of h and b here. I don't even need to make any substitutions. I can just plug these as is into this equation here and this equation there. So my polar moment of inertia about the centroid is just 1/12 hb cubed plus 1/12 bh cubed. That's it. It's the same concept as everything that we were doing, just adding those two together. So for our last problem, if we wanted to find the polar moment of inertia, we would just take those numerical answers that we got. If we were finding the polar moment of inertia about the origin, we would just add the ix and iy terms that we got for our last example, and that would give us the polar moment of inertia.